Okay, teleport ad read. SEW Pod is sponsored by Teleport.
You should probably introduce us first still.
Wait, we're doing the ad read during the podcast.
Yes.
This is
Got
going
it.
right in.
Yes,
Got
we're
it.
just going to start the
Okay.
podcast, and then we're going to talk about Teleport, who's sponsoring our live event. Well,
Great.
our happy hour I'm just going to talk about it now. We're doing a happy hour again at Vegas in the liminal space between Black Hat and DEF CON, like we have done every year for the past 3 years. And it is once again, like last year, sponsored by Teleport. And if you don't know what Teleport is, you probably don't have SSH. But we're very happy that they're sponsoring, and we can attest that Thomas is a Teleport user.
We use Teleport everywhere at Fly. We love Teleport very much. It is a very, very, if you're a SOC 2, it is a very, very good way to get a lot of business processes kind of all tucked under kind of a recorded SSH dealie. Teleport is great. Use Teleport for everything.
And on that note, I'd like to say this is security, cryptography, whatever, and my name is David.
I'm Deirdre.
Thomas.
And today we're talking about Lattice cryptography. We're talking about Lattice cryptography on this very professional podcast with our special guest, Mark Schultz-Wu. Mark, how are you?
Yeah, I'm Mark.
Thanks for being here.
Thanks for having me.
This is like Lattice's Redux, because one of our very first episodes, we talked to Chris Piker about lattices, which was great. He also tried to show us a bunch of slides. And so we ended up talking through what our audio-only listeners were supposed to be seeing, with like a depiction of dots on a field with vectors like that. This is another chance to lattices and try to understand all the stuff that is in the area of lattices and post-quantum cryptography, especially using lattices. And you were posting on the internet recently some very, very useful history of where we started with lattice cryptography, where we started, what got broken, and how we got to things like Kyber, dilithium, and some other fancier things you've done research on. So we would just have you basically talk through what you began posting elsewhere, which is like the history of over 30, maybe 40 years of lattice cryptography.
Yeah. So it's worth clarifying up front. I am a lattice cryptographer. What was this? I think I graduated 2024. I worked with Daniele Michanto. I was working on fully homomorphic, so I do have some background in lattice-based chems, but my publications, with the exception of like one, which was talking about the lattice-based, it's called public key encryption at least, was more on the fully homomorphic encryption side.
Yeah. And that's some of the fancier stuff that, especially if you're trying to do a post-quantum solution to anything that's like slightly fancier than public key encryption or signatures, sometimes you may be tempted to reach for the fully homomorphic solution because it seems to solve your problems, but it might do it computationally costly or largely.
Both computation and bandwidth.
Yep.
So in general, the fancier the lattice things get, the bigger you have to increase one of the parameters, the kind of the modulus, and then you also have to increase the dimension as well. So kind of you can think about like two parameters that like counteract with each other and keep getting bigger and bigger, and then everything gets big, and then that's how you can get like you get FHE papers that talk about 20 gigabyte keys, and it's like, yeah, it's like fine. It's not it's not the biggest keys, it's not the smallest keys. You know, if you're optimizing for size, maybe you get down to 3 gigs or whatever, but it's very far from the public key thing.
Gosh. And I want to get back to that when we kind of we kind of start at the simple beginnings, then we get over there, because then we can talk about like why some of these instances of lattice problems, like they feel a little bit more riskier in terms of like, we think these things when we apply them to these spaces are okay, but then occasionally a paper will show up and be like, oh, anything with parameters that are slightly this far apart, which is bigger than what they are for dilithium and Kyber, basically, or anything more complicated than that are FHE like, get scary. Anyway, so Thomas.
I mean, I have a specific thing here, right? Which is, like, as always, I'm just trying to reinforce things I say on Hacker News. But, like, a claim I make kind of regularly, which I shouldn't be making because I don't know what I'm talking about, is that kind of lattice cryptography and elliptic curve cryptography they're not literally, I think they're not literally comparable vintage, but like they were both live ideas in the 1990s, right?
So
I like to say that there's an
yeah.
alternate universe where lattices win over curves.
So it
And
depends on for what particular applications. The N-true crypto systems, both of them were introduced in the mid 90s.
Right.
And the N-true crypto systems that we see in these days, they're very similar to what was around in the 90s. Like I don't want to say exactly the same, but at least for N-true, I should say N-true encryption, there's a lot of similarities there. N-true signatures from the 90s got completely broken. Lattice-based signatures had a very rough going until like the first secure lattice-based signature was in 2008, which is rather late. The way I like to describe how late it is that fully homomorphic encryption was in 2009. So we didn't get signatures after fully homomorphic encryption, but it was remarkably close, which is kind of wild to think about. You would think FHE is a much harder problem. Lattice-based signatures, they're very well understood at this point, but it took a lot longer to get there because of some additional complexities that show up with lattices for signatures in particular.
so like
Um,
because of post quantum cryptography, there's an attitude that lattice cryptography is like, moon math, like whiz bang stuff, right? And like one of
mhm.
my things is just kind of pushing back on that notion that like we don't
Yeah,
have a good understanding of what lattice cryptography is. Another thing I like to point out is the gap in time between like in true and LWE, or in true and like like New Hope or something like that, right?
yeah.
And like the P curves in curve 25519, right? Like everyone's
So
familiar. Yeah.
New Hope is a great example here. New Hope was in Chrome a decade ago. It was in experimental releases of Chrome. You had to opt in. This was a decade ago. The scheme has had no substantial cryptanalysis in the last decade, no substantial improvements to cryptanalysis in the last decade. When I say that, it's like a decade, it's rounding up a little bit. I think the most recent substantial improvement to lattice based attacks, which was in 2018. When I say substantial improvement here, it's worth mentioning lattice-based attacks usually separate into two components. There's one which is phrasing the problem as a lattice, and then there's the other which is solving the lattice problem. When I say the substantial improvements thing here, I mean the second part, the solving the lattice problem. There have been some iterations on the improving the phrasing things as a lattice problem. If you're familiar with the Matsov attack, this is kind of in its first category. One difficult
Yes.
thing with lattice-based cryptography, which I was actually struggling with a bit today, I was asking some people and getting not that great of responses, is that it's really kind of a socially defined field in a certain sense.
What do you
You
mean?
might yeah, so you might say, okay, lattice-based cryptography, what does that mean? Well, a very easy answer would be it's cryptography based on lattices. Unfortunately, this isn't true at all.
Yeah.
So as an example, the N-true paper, the first N-true preprint, the term lattice appears in it never. Any cryptographer these days would call N-true a lattice-based scheme. If you published a paper on N-true, it would get put in the lattices track, and it was described as a ring-based crypto system initially.
Oh, I mean,
Uh,
okay, I get that. I get that.
yeah.
It like
So
it like reduces to lattices, or like can be
it does
rewritten as a
reduce to
lattice.
lattices, but this is also not a satisfying way to define what lattice-based schemes are.
Mhm.
I mean, one reason for that is like elliptic curve-based schemes don't reduce to elliptic curves; they reduce to polar row on a generic group, right? So maybe you call them group-based crypto, or you call them like polared row crypto. I don't know. Like we don't tend to define problems based on what they reduce to. Um, I mean, for factoring, you like sort of do, but also like you can break RSA without breaking factoring by breaking modular, what's called modular ETH polynomial roots.
Yeah.
Like that does not actually, you do not need to break factoring to break RSA, right? So it's like the name is kind of all over the place.
Yeah.
In general, lattice-based schemes do get broken by lattice-based attacks.
Cool.
And I'm pretty sure that's how the naming for Entru kind of got decided.
I
It was
see.
first ring-based, and then there was a lattice attack on it, and now it's lattice-based. But if we're going based off of schemes that are broken by lattice-based attack, the first one was actually in 1978 with there was knapsack-based crypto systems that Famir famously broke. Um, and so maybe these knapsack crypto systems are lattice-based. I would personally argue they are. My advisor had some papers in the early 2000s on knapsack-based crypto systems. He's a lattice-based cryptographer. So there's a sense in which like lattice-based cryptography is the cryptography that lattice-based cryptographers do, and often involves in kind of reducing problems to solving computational problems on lattices. But
Like other than in
it's
true, check me on this, right? Other than in true, the schemes that we're talking about when we think about lattice cryptography are like remarkably similar, right? Like they're all based on the same basic
I'd say that.
LWE problem.
Well, yes and no. So the popular ones these days are. I'd say that there's two big counterexamples to this, or maybe three. So, as an example, one thing that you might say is lattices are the only way we can get FHE. This is like sort of true if you define lattices in the right way. In particular, there's this problem called the approximate greatest common divisor problem that was popular in the early 2010s. It kind of looks more like a number theoretic problem, like something closer to RSA, but it also kind of looks like a lattice problem if you do lattices a lot, and we can get fully homomorphic encryption from this. And Anton Zhu also has this crypto system he called the Mersini Prime crypto system. I think it was somewhere around 2015. And that also kind of looks like a lattice-based crypto system, and also it doesn't, it's not LWE, it's not N-true, it's its own thing. There's also more recently, there's these lattice isometry problem type crypto systems, which it has lattice in the name, so maybe it's lattice based, but also the first part of any paper on these is always, here's how we rewrite our things in terms of quadratic forms, and now we're going to do everything in terms of quadratic forms, which mathematically quadratic forms and lattices are kind of equivalent, so it's still kind of lattice based, but kind of computationally quadratic forms end up being nicer for those crypto systems. That all being said, the predominant lattice assumptions are almost always the learning with errors problem, or an algebraically structured variant of it, or a variant with rounding, so like learning with rounding, this type of thing, or the N-true problem. There are even more esoteric things than what I've just mentioned. In fact, like when we're talking about, kind of lattice-based cryptography, these are kind of the boring assumptions.
Yes.
One of my favorite things is that there's this line of lattice-based papers which say, we want to do insane stuff, we want to be crazy, and we want to be fast to make a lattice-based PRF.
Oh, yeah.
And I think they're within a constant factor of AES when you have AES NI hardware assumptions.
Really?
Using only AVX2. Yeah, I can't remember the precise constant factor. It might be something big like 5 or whatever, but like you can get very fast PRFs based off of very weird lattice assumptions. These are the spring and leap PRFs.
Okay.
I don't think anyone uses them for anything, but like they use assumptions that are much farther from kind of the boring standard lattice assumptions.
To cover that for our listeners, so we touched on a little bit of N-true originating in the 90s. So that's so let us describe specifically the N-true assumptions, that those things that are consistent with what was introduced in the 90s reduced to in terms of the security definition construction reduction. And not the social construction of like, well, if I can break it using a lattice attack, then why? But like
the N-true, the problem underlying N-true, I've heard people call it as the small decisional polynomial ratio problem.
Okay.
Essentially, you have two polynomials, both are drawn from some small distribution, say some like center, some Gaussian type distribution, discrete Gaussian, who knows. One of them you need to make sure is invertible. Usually invertible mod some other prime than the prime you're normally working with, but it's invertible. And then you take the numerator one, the non-invertible one, and then the invertible one, invertible one, multiply them together, and it looks uniformly random. That's roughly the assumption underlying N-true. And there's some parameters to tweak, which distributions you use. I mentioned that one of them might be invertible mod a different prime, what different prime you choose, but that's kind of N-true. And what I mentioned here, it doesn't really involve lattices at all. You can reduce it to a lattice problem and attack it that way, but the kind of the standard N-true problem, it's about inverting polynomials and multiplying them together.
Okay. And then around 2005, Regev introduced, I think, did he literally call it just LWE, like the crypto system, or
learning with errors? So it's the learning with errors problem, and it actually is a very interesting history itself as well. Which is like, there's this question you might ask, which is that LWE, it's our kind of leading candidate for a post-quantum assumption. You might wonder, why is that the case? And the best answer is, unfortunately, the most boring answer. Very smart people have tried to break it and have failed. But LWE in particular has a very funny story in that the first person to introduce it was one of the very smart people who tried to break it and failed.
Okay.
So LWE originates, and Regev, he has this 2009 survey, I think, that includes this on the LWE problem, that I think includes this point. But Regev was a quantum algorithms person, and he was trying to create quantum algorithms for certain worst case lattice problems. So these
Somehow
things called like the shortest vector problem.
I didn't even realize that. That's neat. That's very cool.
Yeah, well, so some of he's kind of more recently he's switched over into computational biology, but some of his more recent cryptographic work was actually a faster. I think it was a faster factoring algorithm, so some optimizations to Shor's stuff.
Yeah.
So he's
I saw
he's been a
that.
quantum
Yeah.
algorithms guy for 20
Yeah.
years, right? Probably longer than 20 years. But so he was initially looking at these worst case problems on lattices, saying, I want to try to find quantum algorithms for them. And he was almost able to get it to work if he knew how to solve this one problem quantumly. So if he could solve this one particular problem quantumly, he could fully solve, these these worst case lattice problems, which were of independent interest at the time. So with one problem he couldn't solve was LWE. So he said, okay, well, instead of saying I get this algorithm for SVP, also I get a reduction from solving this very particular problem that I don't know how to solve quantumly to, I get a reduction from SVP quantumly to solving LWE.
Mm-hmm.
And that's what the paper ended up being. But LWE really came from a quantum algorithms guy not being able to solve a different problem. And that was like the isolated subset he didn't know how to do.
Cool.
And it's stood up since then. So like, I guess it's a decent way to find a problem.
Yeah. And now we have like a whole lineage of problems and like kind of, narrow definitions of problems that all kind of nest down and reduce to different forms or slightly different variations on LWE. And like,
Yeah.
And I think some of that, I mean, like you have like a learning with errors, like problem or game or whatever, that reduce to SVP, which is the shortest vector problem, or, you've got gap SVP, like you've got like,
Yeah, well, so it's always gap SVP. This is something that's important to get right, because so SVP is an NP-hard problem.
Right, yeah.
So if I said that SVP reduce LWE, if I said that SVP reduces to solving LWE in the average case, that could imply that LWE is NP-hard to solve.
Right.
This is not true, and it's actually not thought to be true.
Yeah.
So when you mention gap SVP, roughly, so how it works is SVP is this problem. You have this high dimensional kind of point cloud. It's this structured point cloud. It's a lattice. And you're wondering which part of the structured point cloud is the closest part to zero.
Yes.
In low dimensions, it's easy. You just do it by looking at the thing. In high dimensions, things, from recursive dimensionality, you might expect it to be much harder, and it is. So
do we have any
if
intuition
SVP
as to why that's hard?
Yeah.
Like I get that like you sit down and like it turns out no one's come up with a good answer for it, but like it just seems like it should
So
be
for
hard,
SVP,
right? Like
SVP itself, no gap, it's just NP hard. So it's, what's the intuition for why it's hard? It's an NP hard problem. Why is any NP hard problem hard? I don't know. They all could be easy. But if any one of them was easy, all of them would be. And we think at least some of them are hard, right? So there is a more satisfying reason for that for these lattice problems in particular. So these lattice problems, or lattices in general, they actually show up kind of in useful scenarios somewhere. So in particular, so coding theory wants to look at kind of high density kind of arrangements of points that are noise tolerant, right? For standard coding theory, this is often noise tolerant in what people call the Hamming metric or pseudo metric, where you get kind of bit flip errors, this type of things. Kind of a particular coordinate is either totally fine or totally corrupted. Another error model you could imagine, kind of instead of this digital error model, you could imagine an analog one where you might have a little bit of noise in each coordinate. This is more accurate for kind of radio communications, this type of stuff. So in this analog noise model, you might say, I still want to be able to code things to get this dense point cloud so I can get efficient, say, radio communications, but I want to be able to efficiently decode things too. So in this way, kind of problems like SVP, more properly the closest vector problem, kind of have this kind of direct application. And this was actually one of the reasons that at least some of the initial computational study of lattices was occurring, was to kind of for these kind of radio communications purposes.
Yeah, I could see that.
Especially since random lattices, for a suitable definition of random, are known to have very good coding theoretic properties. It's kind of like how random linear codes, they're kind of near optimal. Random lattices, for many definitions of lattices, are near optimal for these coding theoretic properties. So if you could efficiently decode a random lattice, then you could get a very efficient analog communication system. This is, for really certain parameters, this is roughly what the LWE problem is kind of efficiently decoding a certain random lattice, which likely has near optimal parameters for these coding theoretic purposes. So none of this is a satisfying reason to say why it's hard. It's sort of close to a problem that's NP hard, but it's in a kind of this parameter regime where that problem is no longer NP hard. The problem's in Arthur Merlin, I think. So if it was NP hard, you would get some polynomial hierarchy collapse. One of those things that people make it kind of cryptography still isn't from NP hard problems in this setting. But then also you have this other community where if they could solve these computational problems on lattices on this average case setting, or in the worst case setting, then they could get these better constructions, and they haven't been able to either.
And one of the things that I sometimes hear referenced, and then if I talk to a lattice cryptographer, they give me like is that we have like a reduction to worst case hardness of like gap SVP for a lot of these LWE systems, which is like not necessarily a complexity result that we have for some of our other cryptographic constructions that we deploy in the real world.
So the answer I have to this is which is that so famously we do have this reduction. This was Rega's 2005 paper for. It was initially a quantum reduction. It was it was made classical, I think, in 2009.
Okay.
And maybe in more generality, like since then, kind of in the more efficient settings that we tend to use lattices, there have been more and more of these reductions. The issue with these reductions is they're what are generally called there's two big issues with them, actually. So one is that if I wanted to use one of these reductions to build a crypto system, I would need to do two things. One is I would need to say, okay, now my hard problem is no longer LWE, it's gap SVP. In the worst case, so that's interesting. But I would now need to figure out what worst case instances of gap SVP look like.
Okay.
I don't think that's really known. So you might be able to do something. You could say like, hey, to figure out how hard gap SVP is in the worst case, I'll sample a bunch of stuff on average and see how it is in the average case. Like it's a fine strategy, but then you're not using the worst case part anymore.
Yeah. Okay. All
the
right.
other bigger issue is that the reduction is highly non-tight.
Oh, okay. All right.
I don't know if people have worked out the parameters, or I've seen a number of papers of people trying to work out the parameters, but there was a lot of debate over which papers did it right. There might have been some errors or whatever. I've seen estimates, I think, as high as maybe 30 or 60,000 lattice dimension to get appreciable security. So it's like
and we're nowhere using that for things like Kyber or dilithium or
no. So Kyber and dilithium are dimension. So Kyber's dimensions like 512 to 1024.
Yeah.
The 60,000 dimension does actually show up sometimes in the fully homomorphic encryption, but that's more even then they try to get away from that if they can. It's more like if you can't optimize certain parameters, you kind of have to have things that big.
Yeah. Okay.
But the trend there is trying to get them smaller as well.
Okay. So basically we have a thing that could be a nice like security like lower bound, except we don't know how to use it to actually give us real world security parameters that are actually useful, that have any relation to that mathematical lower bound.
It's these two things. It's one, it's this non-tightness that you're mentioning, but then the other is that it's not at all clear to me, or I think to other people, that it's easier to worst case cryptanalyze gap SVP than it is to average case cryptanalyze LWE. Because at some point you need somebody to say, I have a computer, I have these algorithms, I tried running them, it took a while, and this is my estimate for how much longer it would take for bigger parameters, right? This kind of explicit work trying to extract concrete parameters from these kind of abstract algorithms.
Yeah. Okay.
And if someone could write down, this is what the worst case gap SVP instance looks like, and this is how long it takes to solve, then we would have something very interesting. But and then also if everything was tight, I should say. But that work is also like I don't know if anybody's looked into it. It seems unclear how to characterize the worst case gap SVP instances that you'd be reducing from.
Got it. Okay. So in the 90s, we've had our very early, social instances of lattice cryptography. Before the 90s, we've got NTRU, which is still kind of floating around in some form. Since the 90s, we get the introduction of LWE in the mid-aughts. And since then, we've gotten these other flavors of LWE, including ring LWE, module LWE, and we've seen these unstructured lattices. One of the crypto systems that uses that is FrodoChem.
That's just plain LWE. So that's the initial version.
All right. For some reason I didn't clock that. I don't know.
So there are so essentially what happens is any LWE instance can roughly be phrased as the following. You have this integer matrix, you have a secret, and you multiply them together, and you add some error.
Yes.
It's worth mentioning this error should also be kept secret, so you might think of it as kind of a static secret and an ephemeral secret.
Yeah.
But that's like the rough shape of it. All the algebraic structure is saying is that this integer matrix, well, matrices take n squared parameters, and that can be a big number. So can we shrink that somehow?
Yes.
You could say, hey, instead of being this n squared matrix thing, I want this to be a matrix that is determined by one of its rows, and then maybe kind of some kind of simple transformation you apply to that row. I might want it to be some sort of Toeplitz matrix, some cyclic matrix, these types of things.
Yeah.
The algebraic structure is all a way of saying that this matrix, instead of being this fully dense one, it's going to be this one with some interior structure. As an example for RLWE, RLWE is usually done over a cyclotomic ring of power 2. This matrix ends up being what's called negacyclic. So you have one diagonal and you have the vector in a column, and then each time you move it over, you kind of cyclically permute
Yeah.
it. Except when you go off one end, you introduce a minus sign.
Yep.
So there is this very concrete way to describe it. The downside is that the very concrete way to describe it kind of can hide some security concerns.
Yes.
I said you introduce a minus sign. That sounds like extra work. Why do that? Why just avoid introducing the minus sign? Everything breaks. So that might sound like a very small reason, like issue you can make that would make everything break. In kind of the fancier math thing, it ends up making a lot more sense. Roughly, you have a polynomial, and if you don't introduce this minus sign, the polynomial has this degree 1 factor, and you can kind of stunt everything down to this degree 1 factor to get a one-dimensional instance that's very easy to break. So the minus
for
sign,
people,
yeah.
For people who like aren't in their happy place when they hear the term cyclotomic field, we're starting with like original Coke Zero LWE with what's now called Photochem, right?
Yeah.
And then we're going to structured lattices where like instead of like a uniform random lattice or whatever, we have structure inside of that matrix, right? Why did we do cyclotomics there?
So why we do cyclotomics there? So it's a good question. You could do other forms of structure. In fact, there was this NIST submission, maybe it was called Titanium, that roughly there's this thing that was called middle product LWE. It's its own thing. It's like there's more esoteric assumptions, but it's essentially said that we get hardness if any of these very large set of structures is fine. So in some senses, maybe it was more conservative, but it's also, I don't remember all the downsides of titanium. It's at least the middle product stuff's a lot harder to work with.
Okay.
But why do we use cyclotomics there? Roughly speaking, the initial thing that was introduced was these cyclic lattices. It's kind of the most obvious thing to do. They had antecedents and they had precedents in coding theory. My advisor actually, I think in 2001, he, not for LWE, but for a different problem, the short integer solution problem, he said we can kind of have this cyclic structure, we can get benefits from it. But then there were these papers that said essentially that the cyclic structure means that when you view things in terms of polynomials, you get this degree 1 factor and everything can break. So you have to split off that degree 1 factor and then you get these cyclotomics. Like it kind of, what cyclotomics are is you take the polynomial x to the n minus 1, which, and then you kind of factor it and you keep the highest degree piece, very roughly. So this x to the n minus 1 very roughly is kind of the generator of this cyclic transformation. So you start with kind of the easiest thing possible, and then you kind of keep the biggest component of it that's secure.
And the primary motivation is to take a secure crypto system, but make the things that you're shuttling around on the wire smaller while reducing to the same problem.
Well, so it's not exactly reducing the same problem. Okay, so the idea is that now you only have to pass around one row or column of this matrix. So you get a big size one. But now it is going to be like you're working over this structured family of instances.
Yeah.
So there are these concerns. Is this structure useful for attackers?
Yes.
It's plausibly true.
Yeah.
And so RLWE, so the RSys, so it's kind of the short integer solution version of this was introduced in 2001. RLWE, I think, was roughly 2011. The structure has finally helped attackers this February, maybe.
Oh.
I think they got a times 4 speed up, and it seems kind of limited to that. So it is there now finally appears to be a very small gain from the structure, but it has taken a while to materialize. It is worth mentioning for kind of adjacent lattice problems, the structure can help. So I mentioned you have this matrix and you have a single column and you kind of apply this transformation. You can think about like having this one structured block in it. Kyber does something different. Roughly, it has smaller structure blocks, say 256 by 256 structure blocks, and then it builds the block matrix out of that.
Right.
And this
Yeah,
is
yeah, yeah.
module LWE.
Yep.
The reason why we often prefer module LWE versus ring LWE, and I say often because this is only true in public key cryptography.
Right.
In fully homomorphic encryption, everyone uses RLWE.
Mm-hmm.
But the reason for public key cryptography why we do that is that in 2016 there were some improved quantum attacks against kind of these single block instances, not of ring learning with errors. So the attacks, I think to this day, don't really say anything for the deployed schemes.
Wait,
But
wait, 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 wait,
yeah.
wait, 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 wait.
Yeah,
Modular LWE is just LWE with block matrices?
roughly. Yeah. So
Yeah.
it's module. Here, module, it's the
Module,
semantic
yeah,
term.
module, sorry.
Yeah.
Yes.
Yeah, but it's roughly just you have block matrices and they all share the same structure. So
This is this thing where
either-
like, you look up like modules in Wikipedia
Yeah.
and you get like,
no, it's impossible. Yeah.
right.
Like
The actual thing that's going on here is it's just block matrices?
it's block matrices, yeah.
Yeah.
So it's block matrices, and then it's you instead of fully materializing that, you only ever materialize like the single rows you need, and then you need to have an efficient way to multiply these block matrices by a vector, and that's where like NTT stuff can show up.
Yep.
You know, so it's
This
a lot
is
of
my
it can
thing.
be easier in terms of polynomials, but it's block matrices.
This was my understanding, which is now like devastated by the last 15 minutes that you two have been talking, right? My understanding before, because I'm an idiot, was that all of the complexity in these systems, all the structure that was being introduced was about something like NTT. It was just about like speeding up the multiplication.
Well, so that also shows up. So it's not independent, because if I just have this dense matrix and I have a vector and I want to multiply them, that's n squared time, right?
Yeah.
But if I have a structured matrix here, and then I will have, if it's structured in the right way, say it's an NTT matrix, and then I have a vector here, now I can do something n log n.
Yeah.
Right.
Yeah.
So roughly speaking, it kind of does both in that we get the compactness because you only need the single row or column. And then also we get this kind of NTT friendly form.
Yeah.
So we can also get some computation speed ups.
Yeah.
Okay, so like module LWE has become, for reasons, very salient in like discussions about risk in lattice systems. But
yeah,
I interrupted you to say, you know, for fuck's sake, about modules and block matrices, right as you were going to say, we now prefer block matrices, or we now prefer module LWE. So I would like to hear more about the thing you were originally going to say.
Yeah.
Yeah. So what happened is in 2016, there were quantum attacks, I think, against ideal SVP.
Yeah, that rings a
So
bell.
I mentioned before that SVP is what reduces, worst case SVP reduces to LWE. So you might think, oh, these quantum attacks against SVP, that's concerning for LWE. Well, not really, because the reduction goes in the wrong way. So if you want to solve LWE, you have to reduce to actually what's called a rank 2 instance, kind of a block structure with like 4 squares instead of 1, right? You have to reduce to a rank 2 instance of ideal SVP. And the quantum attacks don't help in that setting. So in 2016, these quantum attacks in a relevant but adjacent context showed up. People were like, hey, it's not that much worse to just use this block structure. And then we're kind of farther away from the issue. And things have been fine since then. But also for RLWE-based schemes, things have been fine as well. So as I mentioned, fully homomorphic encryption still uses RLWE everywhere. It uses RLWE with insanely more speculative parameter sets. When I mentioned there was this ×4 speed up from the algebraic structure that appeared recently, I think you get much bigger ones in the FHE setting. I think that there was maybe a 15-bit speed up. I don't remember. I'd have to check again. But that's because FHE people do much, much more speculative things, to try to get things to be more efficient.
Yeah, and this kind of leads into, this is like there's the boring crypto stuff, which is literally like the primitives that are basically public key encryption that you twiddle with an FL transform and turn into something that looks like key exchange, but it's not. It's a chem, and then your regular schmegular, signatures to give you like unforgeability or whatever you want to do. But things that get more complicated than that have to go into these settings that have a little bit more exotic assumptions if you want to
Yeah.
do.
Well,
Yeah.
so I would actually say lattice-based signatures do tend to be a little bit harder than fully homomorphic encryption to get right,
Oh,
which again
okay.
is a very funny sentence. But
Tell me
yeah.
why, because I would never even have like that notion
Yeah.
wouldn't have even entered my head.
So there's roughly two families of lattice-based signatures. One of them I'm more familiar with. Roughly what they do is to say, okay, so lattices looks a little bit like Diffie-Hellman. If you
Yeah,
think of it
yeah,
as AS plus E, if you just ignore the error, AS, it's like, I don't know, it's like a one-sided group action.
yeah.
It's like Diffie-Hellman, right? So you can do Diffie-Hellman type things. In fact, Kyber and things like this, they can be thought of as a Diffie-Hellman type thing that adjusts for this noise being here.
Yeah.
So if you're doing Diffie-Hellman type things for encryption, you could say, hey, for signatures, I also want to do not Diffie-Hellman type things, but I want to do standard things. So maybe I'll do Schnorr signatures or
Yeah.
something like that.
Oh.
And a lot of people try to do this, and all of them break because this noise here ends up being much more devastating.
Huh.
In particular, I mentioned before that the noise, you can think of it as an ephemeral part of the secret. So
Yeah.
the noise is security sensitive. So lattice-based signatures, until they started to be done properly, would often leak this noise. There would be attacks that would allow attacker to recover part of the noise. If you recover part of the noise, you can almost always break the scheme pretty easily.
Yeah.
Can I just ask real quick what that attack looks like? Because this is like one of the rare instances where I have like a bit of an intuition for what that would be.
Yeah.
But like, okay, so like I can see immediately why leaking any of the error bits in an LWE computation, like the whole reason why this system isn't just Gaussian elimination is the error, right? So like obviously
Yeah.
bad to leak it. But like what does that attack look like?
So I'm pretty sure they ended up being machine learning-ish type attacks, where the idea is that if done improperly, you get part. So lattices, they're these. I mentioned they're these point clouds, and you might imagine for these points, there's kind of this initial block, and then everything is a translate of that, right? So the kind of the inside of this initial block, you might call the fundamental parallel type bit, or at least lattice-based cryptographers do. So the attacks roughly would say that we can identify leakage somewhere within this fundamental parallel piped, and then maybe it was some sort of like gradient descent-ish type attack on top of this with enough signatures to recover the actual secret, and then from there you win. It's something along these lines. There's
Okay,
been
but it's much more interesting than the hidden number problem then, right? It's not like we have a bit of bias and then I can literally just do like a a BKZ or something like that.
I think that there is this kind of like averaging step you have to do. I don't think you just create a lattice, and I think you do need many signature samples.
Okay. Oh, so
Um,
you do need like one key, and then are we doing
I don't know if there are attacks with a single signature.
right?
It's not a huge amount you need. I think there are papers I've seen that have been like on the order of 500, but
Huh.
it's something that like it's devastating attacks. You need to get this part right with lattice-based signatures. But that's why if you look at stuff like dilithium describes itself as kind of fiat Shamir with aborts
Yes.
scheme.
Yes.
The fiat Shamir is as part of creating the Schnorr signature. The aborts is to say that hey, if we would leak part of this error, we try again until we don't leak it.
Oh, that's fascinating. That's where that comes
This is
from.
still this is getting more. So what is what what's happening when we're doing the fiat Shamir in the Schnorr signature that's causing us to leak the error? This is like because I don't do signature stuff.
I'm pretty sure it's that the errors get too large. The rejection conditions in dilithium are bounding the size of the error. I think there's two rejection conditions actually, but I think that there was this paper a couple of years ago that said you only really need one of them, but that one is load bearing. Although this wasn't for dilithium specifically, it was for fiat Shamir with aborts type schemes.
Neat.
I'm
That's my contribution.
Okay, so for in more exotic settings like FHE, why do you have to get more exotic, and why are your parameters slightly different than the things that we might see in Kyber and dilithium? And why are your assumptions more exotic as well?
So there's a number of reasons for this. So the first thing is I said FHE always uses ring learning with errors, not module. The reason for this is because of something people often call like I don't know the seed compression,
Okay.
where an RLWE ciphertext has two components, A and B, and the A part is uniformly random. So you can just store a small seed there, and you can use like an XOF or something like that to expand it.
Yeah.
For MLWE, you kind of pick up more of these components in the front, so you would need kind of more of them. You could all generate them from a single seed. So in this setting where you can expand things from seeds, it doesn't really matter. the issue is this expanding from seeds thing does not survive any homomorphic operations.
Wow. Okay.
So even something as simple as adding together two ciphertexts, well, now you have that, an XOF of seed 1 plus XOF of seed 2. You can't find a seed that really expands to that target. So you now have to store the full two polynomials here, and in the MLWE setting, you have to store even more, right? So that's kind of the for FHE, you end up taking this big size hit, this big bandwidth size hit, if you end up using MLWE versus RLWE.
Okay.
But there's other more exotic things people do as well. And it's worth mentioning when I say for FHE, there's two broad classes of FHE schemes. There's what's often called FEU or TFHE based schemes.
Yeah.
And then there's generally CKKS, BGV, BFE. They're all kind of tensor product multiplication schemes.
Okay.
So for this first class, you get a lot more flexibility. You can do things much closer to public key type crypto. But the second class is the one that I'm describing that has less flexibility. In particular, for the second class, you get these weird assumptions about the error. So in public key cryptography, the error vector, you can kind of choose to be from any distribution you like, as long as it's not too concentrated.
Yeah.
If it's too concentrated, there's these attacks from 2011, the Aurora Gay attacks that start being applicable and concerning. But even things like often people do Gaussian type noise with standard deviation 3. That's not too small, right? Gaussians are a little bit hard to generate, especially if you need to have a mask implementation of the generator. So instead, you can actually just sum up a bunch of bits. It's a binomial random variable. If you center it, it looks kind of Gaussian, and it's good enough for encryption. So the issue with this is that there's this one component of FHE that's very key, where kind of a certain parameter scales with the sum of all these the sum of the absolute values of all these coefficients. So instead, FHE likes to have this noise be kind of sparse ternary noise. They want to make this as small as possible, which is a much more aggressive assumption for a particular reason. In particular, the error distribution and the secret distribution for LWE, they tend to be fine with anything. We have these proofs that as long as they have enough entropy, you can get. So there's a setting called entropic LWE, where there's two relevant things to say. I should say. The secret distribution and error distribution, they can be the same. And then as long as the error distribution has enough entropy, things are mostly fine. But the worst case to average case reductions aren't true in this setting. So even though we don't use them for any choice of parameters, moving to settings where the worst case to average case reductions are no longer true is still often seen as something that's very concerning.
Okay.
Just because
because you're never quite sure how your parameters may break down, and then at least you have that as a backstop kind of deal.
It's not like that. It's more that if you're in a regime where the worst case to average case reductions hold, then you kind of have this understanding that it's hard for there to be atypical structure there that wouldn't also help in the gap SVP world.
Okay.
It might help with much smaller gap SVP instances, but an algorithm here is concretely an algorithm for gap SVP.
Got it. Okay.
Right. With the caveat of this tightness being bad. But if you start falling outside of this worst case to average case setting, then there could start being non-trivial attacks that wouldn't also imply an attack for gap SVP.
Okay.
So in FHE, the secret distribution can often end up getting much weirder with much more aggressive assumptions. I've seen papers that suggest Hamming weight 32 and Hamming weight 64 secret keys, which are very small numbers, although I don't think there have been attacks on these schemes. So, but there's also the ciphertext modulus can get very large in FHE. Roughly for Kyber, the ciphertext modulus is 14 bits. It's relatively small. In FHE, for at least these tensor product based schemes that I was focusing on, each time you do a multiplication, you kind of have to shave off 50 bits from your ciphertext modulus, very roughly. So if you have this complicated circuit, you need to compute, say, a bootstrapping circuit, then you might need to support 800 bits, 1500-bit moduli, things that are much larger than the 14 bits that Kyber uses.
Yeah. We need some big limb arithmetic, and all of this has to be prime.
So you can usually it doesn't have to be prime. That's one of the benefits of all of these LWE based schemes is that the number theoretic structure of the moduli does not really matter at all.
Oh, good.
So as an example, I think Kyber is prime, but it doesn't
Yes.
have to be. I mean, Saber was another NIST finalist, and it's 2 to the 32, right?
Hmm.
So it doesn't really matter.
Okay.
For FHE, they take a bunch of word-sized primes and they multiply them together. So they do CRT-based things, but you could do plenty of other things. It doesn't really matter.
Cool. Wow. Okay. So we've basically done a whole tour of the history of lattice-based cryptography, including some of the whiz-bang stuff that, depending on your field, you may see some FHE stuff or things that use FHE constructions under the hood, such as like
Well,
blind.
they are being deployed practically, generally not full FHE schemes,
Yeah.
but I think Apple's caller ID uses homomorphisms of lattices.
I
So
wouldn't
it's like
I wouldn't be
it uses
surprised.
very weak homomorphic lattice-based stuff.
Yeah.
And I think Google might have something as well, but I forgot.
Yeah, those are the areas that I expect more things to kind of trickle out, because like things that we might have used blinded commitments or other things using elliptic curves basically are right out if you're trying to deploy anything that might be quantum resilient into the future. And then you start reaching for lattice things that generally might have something FHE-ish under the hood. You're just not doing a full, you know, like fully homomorphic computation with a bunch of other fancy stuff, but under the hood, that's, you know, if you're trying to do anything with homomorphic commitments and doing anything with that, like that's secretly full, you know, homomorphic reductions underneath it, and I expect more of those to show up.
Yeah. It's also worth mentioning it's not purely a quantum pre-quantum thing.
Right.
So a lot of FHE applications actually don't particularly care about the quantum security aspect of things. It's like even in these kind of relatively simple settings, lattice-based things tend to be very fast.
Oh yeah, that too.
So
Yeah,
like
because
they're the only real cryptography we have that I've seen some people describe as, you know, quasi-linear time, where, you know, the the compute kind of almost scales linearly with just the size of the things you're operating on.
yeah,
It's
it's
not common.
and like you could make an argument that in terms of trying to find quantum resistant, you know, replacements for the stuff that's like the boring crypto that's deployed a lot all over the place, like key agreement or the equivalent of key agreement and signatures. That's kind of why they win, is because they're very fast and they're quantum resistant, and they generally are small enough to fit in a lot of places. And a lot of the other cryptographic problem lineages just don't seem to fit for one reason or another. But yeah, there's other problems that like there just isn't even equivalent, like the fully homomorphic stuff.
Like when you put quantum into that mix there, it's kind of obvious why it's so attractive right now. But like there's a I don't know the answer to this question, but there's a reason that we ended up using curves and not in true back in the 90s. Right, like, and
Yes,
I
I'm
mean,
not entirely sure.
part of it is
N-true did
part,
have
part of
some
it is that we didn't care
patents.
about quantum then, but like,
I mean, equivalence of
Yeah,
Miller was like late
so if it's
80s.
in the
So you've
90s,
got like a almost 10-year head
yeah,
start.
so N-true was mid 90s, so it was a little bit later. It had some patent encumbrances. I think what's it called? Elliptic curves did as well, but
They did,
the
but
N-true ones would have been earlier. Sorry, not early. They would have been the patents would be expire later in the future, I should say. I think, how to say, it probably also didn't help that the entry-based signatures were broken pretty quickly, right?
yeah.
So I think they were broken before 2000, so that would make N-true encryption look a lot more suspect. These days, it seems mostly fine, but there have been non-trivial attacks against N-true that are not possible against RLWE. So there are some concerns to have against N-true, but it
right,
hasn't
like
impacted the public key
original.
cryptography parameter regime.
Sure, like also the vibe I have is that like just LWE has like a clear kind of theoretical basis for it. Like LWE is
a clear
it's a
theoretical
cleaner
basis, yeah.
abstraction, right? I'm
Yeah.
more. I think I'm more just like there's sure, like we had reasons to trust curves more than we had, you know, and true or whatever, like that now happen to be considered lattice. But like there's practical reasons, I assume, right? Like 'cause nobody was thinking this, like no one was thinking this carefully. I was there in 1998.
Yeah, so the main things that I would say for practical reasons, or at least why lattices are more appealing now, lattices, there are a bunch of, you know, this matrix vector arithmetic or rephrasing in terms of polynomials. So they if with vectorized multipliers and vectorized adders, they kind of take advantage of that vectorization very well. That probably wasn't as relevant in the 90s. Lattices are bigger, so that's a clear downside. Um, and yeah, I like those are the big downsides that I know that I know. Like I don't know how fast lattices are compared to elliptic curves if you remove AVX instructions.
Oh, they're
They
faster.
are
They're at least
okay.
the Kyber LWE stuff. You don't even need speed up. Like maybe you would speed up your hash function, but that's independent of the lattice.
Is this on architectures like are it, lattices auto vectorize relatively straightforwardly in many settings as well. So this is ensuring no AVX instructions to
Yeah,
through.
like
Yeah.
even
Okay.
even naive implementations with no vectorization are very fast. And you might have
Yeah.
to do some tricks. Maybe in like 128 versus 512 for like if you do Kyber 512 versus say P56 or something like that, or X25519. The X25519 might go faster than you, but you've had some good optimization tricks added onto that for a while. It's not
Right.
it's
And we're
not
also
difficult to do a very fast, naive, non-vectorized assembly or intrinsics LWE Kyber.
sure. And we're
One
fully curve committed before curve type before 25519 happens. We're already like the P curves one, like
Hmm.
Yeah. The,
one other
and
relevant
true
thing
is not in the mix.
I don't remember the initial parameter sizes from Entru, but so there's Entru wasn't initially phrased as a lattice-based crypto system, but quickly it was determined you could reduce it to a lattice problem and then attack that lattice problem. Algorithms for attacking lattice problems did have substantial advances between 2000 and maybe
Hmm.
2015, 2018, somewhere around there.
Hmm.
So the security story for Entru like probably didn't look that great as those advances were happening.
Hmm.
I don't know. Again, I don't know what parameters they initially chose, but if they chose parameters aggressively enough, they probably would have been broken, even if current parameters are probably
I
Mm.
fine.
mean,
Yeah,
Okay,
I'm
like
seeing
so
some
NIST curves,
sample params. Yeah, go
like the
ahead.
timing just doesn't work out. The NIST curves were being standardized in like 98, 99, and you have Andrew coming
Hmm.
out in like 96, right? That's just not going to fucking happen like on that timeline, no matter how good it was. To say nothing of the fact that we couldn't do signatures with it, like,
Yeah.
and
okay.
Well,
elliptic
not only
curves
we
were like
couldn't
the
do
hottest
signatures,
thing
we
in the
tried
world
signatures and they
because of
broke.
Wiles at the time too. So
Which again, I could do a full hour just on attacks on naive Schnorr LW signatures or lattice signatures because those attacks are really neat. So I'm gonna short circuit this a little bit and just say simplified and true prime.
Hmm.
So S and true P versus original and true. Where are we?
So how to say this? I'm SNTRU-P, I would describe the following way, but I haven't looked at the original NTRU scheme as much. So SNTRU-P is roughly the following. And when I'm saying here, this story also was replicated in the LWE land. Like roughly, there are three ways to build lattice-based chems. You kind of start with your pseudo-random component. It could be the NTRU assumption. It could be LW assumption. That pseudo-random component kind of has this secret part. It's not good for anything public key. The initial thing people did, at least in LWE, is you would take this randomized subset sum of it, and then the random coefficients from the subset sum, you would have that be another secret. And then this kind of is roughly the two secrets, sort of. So this you might call leftover hash lemma-based construction, because for its security, you need to appeal to something called the leftover hash lemma. The other thing that you can do, at least in LWE land, I don't know if this works for Entru, is instead of doing this randomized subset sum that needs these leftover hash lemma type constructions, which the downside for them, they obtain this stronger form of security. They obtain kind of a statistical indistinguishability of, or they don't obtain that form of security, I should say, but applying this step to kind of make this randomized sum look uniform again,
Mhm.
that this requires this single part of the reduction is statistically secure. So the parameters chosen for are maybe a little bit larger than you
Mhm.
might want.
Mhm.
without impacting positively your total and security that you get.
Mhm.
So instead of doing that, you can actually do this other second application of the LWE assumption to get something that uses slightly smaller parameters. Both of these, they create this kind of random pad that's agreed to up to these lower order errors, and you can add messages to it, do a one-time pad type thing. The final thing you could do is you could just say, hey, I just want to build a chem. I don't actually care about messages. So you could have this random pad and you could just apply some shared function to it that will agree on the key. So this type of third thing, this is closest to what SNTRP does. Although from entry, you can also build directly public key encryption. So you could do these other constructions as well, at least a variant of the leftover hash limit thing, I think. So there initially were these LWE-based things that looked closer to SNTRP that didn't have this explicit message and followed this paradigm. But they ended up not being as popular in the NIST scheme, in the NIST competition. I think New Hope initially was of this form, but they changed it. And I don't think any finalists ended up being of this form. For LWE in particular, it's hard to make the resulting chem CCA secure. For NTRU, it ends up being easier to do. So you can get SNTRU-P CCA secure based off of kind of taking this NTRU assumption and then what's it called? I'm assuming they don't do this leftover hash limit type thing, but you don't include this message. You apply this decoding stuff to get a shared quantity, and then to get CCA security, because isn't any. It has a more straightforward path to CCA security.
So, like, the subtext of that is kind of like, obviously, if you're a nerd, right, is that, like, in the IETF and in NIST and all that, there's basically a drama between module LWE and Kyber and SNTRP, right? Like, SNTRP was implemented in SSH originally. New Hope, which is RLWE, I guess, was browsers before that. But there's key implementations of all these things, and then like module LWE is like the standard now, right? And SNTRP is like, I don't know what you would call it, like, but it's the other system that people think about or advocate for. And so like the big debate, especially among people who don't do this professionally, is like, are we taking a huge risk flyer on using module LWE as opposed to using something like simplified untrue prime?
I'm biased, being a fully homomorphic encryption person. Entry is not
Good.
secure in fully homomorphic encryption anymore. It is for these TFHE few type schemes, but in 2017 there was a non-trivial attack that applies only to Entru that breaks it in every parameter regime I care about. So maybe it's more conservative, but that's only from a certain definition of the word conservative. In applications I care about, I can no longer use Entru, even though it has appealing computational properties because it's explicitly insecure. So.
But non-FHE for just regular public key encryption.
The thing is, non-FHE, this attack did not get down further, right?
Okay.
But it's this type of thing where it's like, let's say McLeese. People like McLeese. I mean, people like McLeese. Some people advocate for McLeese, right? And one of the justifications people give is that it showed up, in 1978, and it's been secure ever since. But in the last few years, it's not been true. There have been these series of papers that have said, hey, there's maybe this additional structure in McLeese that can be exploited. And it's, I'm not sure the current status of the papers, but at least the abstracts are getting pretty concerning, right? So whenever there's this like additional structure showing up, it's something that gets a little bit concerning. Arguably, this happened for Entru in 2017 with these additional attacks on FHE. It also arguably did happen for RLWE with these attacks, these quantum attacks on this adjacent scheme, right? Or on this adjacent assumption on kind of ideal SVP, but not the rank 2 version that you would need to break RLWE.
Right.
So there are like these things where it's like, whenever I see one of these kind of non-trivial attacks on something adjacent, it's like, well, can it move over? Is it something to be worried about? So I would be a little bit worried about RLWE and a little bit worried about Entru for both of those reasons. So
I mean, that's also that's literally the logic of safe curves, right? It's like, here are adjacent attacks on specific curve structures that only matter in specific regimes, ergo never use these curves, right? And it's like, it seems like that's essentially the same argument here. It's like,
yeah, so it's,
I mean, it is in the year of our Lord 2026. But Mark, are you trying to like hint towards, yeah, I don't know if I want to use those assumptions anymore, because what if they keep moving? What if those attacks keep getting better?
It's mostly that. Well, it's in my day-to-day job. I just explicitly can't use
Right.
untrue,
Okay.
right?
Right.
And it's that if I a lot of this is kind of vibes based in the sense that if you look at
A
the
lot of
threshold for where we think
cryptography
it's safe,
is vibes based, honestly.
yeah. But if
Like
you look at the
lots of
threshold for
it.
where we currently think it's safe to use true versus not true, I think it's if you have this ciphertext modulus q, I think of its q being roughly less than 1 over 100 n to the 3.2 something, or maybe it's some arbitrary number. And arbitrary numbers appear plenty of places. The best lattice attacks have arbitrary numbers in the exponent. So it's not like arbitrary numbers should just totally disqualify a scheme from being used.
Mm.
But then also it's like I would feel more confident if there was some clean number being like, oh, and the attacks can't go below that because
Yeah.
it's this clean number. So
Okay.
I want to just compare and contrast a little bit back with elliptic curves, just in terms of like timelines and analysis. Like you have Koblitz and Miller being like, let's do elliptic curve Diffie-Hellman in 87.
1985. I always thought it was 85.
85
yeah.
when they wrote the paper, 87 when it was published, right? And then NIST standardizes that in 99, 2000, meaning there was some sort of lead up to that. Now, we're much, much better nowadays at writing cryptographic standards than we were then, despite the best efforts of NIAP. And but like if you go back and you look at like what were all the problems with like cryptography in the 2000s and 2010s, they were by and large not with the primitives of that era. They were like these standards all are written poorly, and like some of these protocols were dumb, or like the way in which we chained AES together was a bad way to chain AES. But like primitives were more or less held. And you like look at P256, like we're still using today. It's not quantum secure, but that takes 10 to 15 years to get standardized, and then another 10 years for adoption. You look at lattice-based cryptography starting in the 90s. 10 years later looking at ring LWE, and 20 fucking years after that is where we're at now, right? Like
Yeah.
I'm not a primitives person. I'm not picking parameters for these things. My job in the last basically decade plus has been to listen to people who do work on primitives and figure out how to use them in the real world and if they're being used correctly. And the answer is people have been like looking at this stuff for longer than elliptic curves, like at the time that they were deployed. These are a safer thing to move to. And like if you are familiar with like Diffie-Hellman and cyclic group based like cryptography, like I encourage you to go to like your preferred AI chatbot and say, I understand Diffie-Hellman, explain to me enough like algebra to understand Kyber. It will do it very good. I did it earlier today.
This is literally what David did before this
I
episode.
did it like earlier today because like again, actually understanding like all of the details of the crypto systems is like not relevant for day-to-day use a lot of the time.
Yeah.
I'm just waiting for the IETF post where they say David Adrian, who just learned how Kyber worked 5 minutes before shooting this episode.
Because it turns out that like part of this is like evaluating, experts on various things and making decisions, and like that's the way it goes. And I think we're actually at like a very conservative point of using lattice cryptography. Like post-quantum cryptography.
yeah, I think something
Lattice.
I think something that's not appreciated often by people who are concerned about lattices. Like I've seen a lot of arguments that I have a hard time following. Like people have mentioned dual EC was bad, so we should be concerned about LML chem.
Everyone knew dual EC was bad, but when they first suggested it.
But so this is true, if the potential for a backdoor was known, and then also not only that, like if default parameters weren't published, I don't know if dual EC had any issues. I think the issue was both the potential for backdoor and default parameters being published that were the backdoor parameters. But even ignoring that, if for lattices very early on in I think it was in Lattice Cryptography, the internet, there's this section that says, hey, backdoors are bad. This particular component of the scheme could be a backdoor. We're going to throw away some efficiency to make sure that it can't be leveraged. And every scheme since has always done this. Like it's, lattice-based cryptographers also want to build secure systems, and it shows up in the constructions. But not only that, like there's this like the concerns over the NSA and potentially backdooring or subverting cryptography with lattices are a little bit confusing, just because it seems like everyone else is moving over to lattices too. So Europe, for the most part, has also chosen lattice-based schemes. Not always the same schemes. The BSI, so the German InfoSec government group, have chosen Protochem, I think.
Yeah.
The Chinese are not. They have not yet announced what schemes they're going to be moving over to. They're rather early in their process. I think a
Yes.
couple weeks ago they had the final submission period for their schemes closed down. But the comments that you can see from certain Chinese cryptographers make it seem like they're going to be going for lattice-based schemes. They're going to be lattice-based schemes with Chinese characteristics, which for Chinese lattice-based schemes, there was a NIST submission lack, which is maybe good to look at. It was doing something roughly Kyber-like, except it chose a very small modulus, 8 bits instead of 14 bits, and it tried to argue that by doing some error correction argument, you could get things to work. It got broken. So the issue for why it got broken is somewhat technical, but roughly the Chinese response to it appears to be that we're not going to do lock again. It got broken. Instead, we're going to switch to an unstructured lattice-based thing. Maybe because they're worried about the algebraic structure, but also because the algebraic structure is specifically what made this error correction component of lat break. So another way to fix that is just use a larger modulus like Kyber does. So it might be that either one. It's hard to tell.
But like in the BSI case, and I guess in the Chinese case, if they do unstructured lattices, right? Like if you're using Protochem, there really is an argument there that,
Well,
that's
they
a
wouldn't
more
use Protochem exactly. I think they
right.
What is it? I think it's S Cloud Plus. It's really like it's more like a Protochem version of this black scheme, which had some roughly, how does this describe it? So in lattice-based schemes, you have this error, and when you decrypt, you get the message plus the error back, and you have to remove the error. Almost every scheme, you just round off the low order bits. That's where the error was. You're fine. You could say, hey, handling errors. That's like what error correcting codes do, or that's what like these types of things do. I can do something fancier to be able to tolerate more error and then choose smaller parameters. This is roughly what LAC did, and it is roughly what SCloud Plus does versus Photochem.
Okay,
so
like
it's a little bit different,
but like if you collapse it down to just like the German case, right? Like the Photochem decision there really is more conservative than the Kyber thing.
So it depends on what you mean by conservative, because it's like if I wanted to make AES more conservative, would I design a new block cipher, or would I say AES with 1,000 rounds? Right. Well, the new block cipher, I mean, it might be good, but AES with 1,000 rounds, ACE would have to be really weak before 1,000 rounds is broken. Right. So conservative usually in cryptography means within a certain efficiency budget. Right. So for Protochem, is it more conservative, or is doing Kyber, but doing Kyber with modular rank 15 more conservative? I mean, it's hard for me to say. If you're saying the downside for Protochem is the large ciphertext, and I have this large ciphertext budget for being conservative, is it better to use an LWE scheme versus MLW? I just don't know.
Yeah.
That's good. That's a really good way of framing it. That makes sense.
Yeah.
And I will say, if you are a country and you are trying to get me to care about your cryptographic standard, you need to have at least twice the GDP of California for me to start reading your standard. We're just going to set that as the bar. Looking at you, Germany. Also can't.
I wanted to I wanted to also shout out South Korea that also did a PQ crypt competition, and they also selected lattice-based chems and signatures. I think there was Smaug and another one. But they're slightly different. They have slightly other assumptions, but it was kind of like looking at what came out of the NIST competition, and we're like, oh, we can make some tweaks to some of these things and learn some stuff. We'll see if they get implemented and deployed in anywhere.
Yeah, there are many different choices that you can make with lattices. I mean, even the NIST competition, like the final 3 lattice schemes, you really could have chosen most of them and gotten something mildly different and probably fine. But it does seem like essentially every country I've seen that runs a standardization, or at least every appreciably large country that runs a standardization, is kind of converging on lattice-based things. And I'm sure this has some downsides. If lattices end up being weak, that's bad for everyone. But it also, like, for this kind of argument that the NSA is trying to standardize weak cryptography, it's like, okay, well, why is China going along with it? Why is it makes it a little bit more confusing of an argument.
Right. Although the freaky argument online, or the freak argument online, is just that like lattices are fine, modules are the problem.
Yeah, but in that case, if the NSA is saying, "Hey, China is doing unstructured lattices, and we're going to do modules," it seems like they're intentionally doing bad
Yeah.
things in like that geopolitical fight. You know?
I'd be remiss to not forget about Falcon, the future FNDSA, which we're totally going to
Yeah.
get a draft standard for any day now out of the Department of Commerce. Do you have anything to comment on these floating point based
Yeah,
lattice schemes?
I I I'm uncomfortable with it. I don't know. Like it's really small signatures. That's great. I'm sure some people will do it right. It feels like something that's very easy to get wrong. But maybe I'm pessimistic.
You're
I don't
not
know.
you're not the only one that's just feeling a little about implementing Falcon securely.
Floating
But
point
okay.
numbers aren't real. They can't hurt you.
I mean, they can hurt me in secure implementations of my cryptographic software. So that's
Wait, how do you even handle constant time Falcon with subnormals?
a
Or
good
You
like I know that
don't.
there's
You
question.
don't.
been
So it was just DOA. There is maybe one
Yeah.
person in the world that understands how to handle constant time floating points, and it's not clear if
Yep.
anyone else understands what
Yep.
they're saying or will be able to duplicate that.
Yep. Yep. Exactly that. You literally clone like one person and stick them in your
yeah.
lab.
Okay, so what have we learned today? I've learned that Oded Regev, who is the godfather of all lattice cryptography, is now a computational biologist.
Yeah,
Oh
I'm
my
He
pretty
saw
sure. Like
he
like
saw this coming and exited the field.
yeah, I have no clue why he switched over. And it's not purely computational biology. He actually writes mathematical lattices papers as well. That like he had a paper that got into the Annals of Mathematics recently. So it's like, you know, one of the best math journals in the world. So he still writes lattices papers, and he still does quantum papers and computational biology. And
Makes
yeah,
a
This is
ton
very
of
interesting to
sense.
me
He's
because
just
my son is
excluded us,
yeah.
the terrible group of people. Like, I don't want to be at these NIST things.
yeah.
My son is a grad student and an aspiring computational biologist. So this is I don't know,
Ah.
it gives me a thing to talk about with my son. So you've healed my family.
Glad to hear.
I've learned that you really, really need to get a quantum algorithmist to build your cryptography because that's going to stand the test of at least 20 years where other people fail. And you just have to catch them before they turn into a computational biologist.
And a couple
So I
hours
learned you
ago,
should
I
definitely
learned
ask
how
Chat.
Kyber works. So, you know, we're all learning
Yay!
something today.
I think everybody should go on ChatGPT and just ask it to spell out how a attack on a naive LWE Schnorr signature works
Oh,
because it's a
yeah.
neat attack.
Yeah.
It's a neat, like, just the blueprint or the schematic of that attack is pretty neat.
Well, we want to talk a little bit more about that in a second. I want to give a shout out to Alfred Menezes, who is, you know, one of the OGs of elliptic curve cryptography, has been cranking out a whole series of lectures free on YouTube on his YouTube channel. We'll put the link
Horticulture.
in the notes on post-quantum cryptography, on a whole bunch of cryptography, free and available. It's amazing and it's pretty cool. So if you'd want to learn how Kyber works and how a lot of these last crypto schemes work, that's a good place to learn if you don't want to turn to your local large language model to do it. Cool. Anything else?
It's also worth mentioning.
Yeah.
So Menzies, his the paper showing that regev's reduction is not highly non-tight,
Yeah.
so could never really be possibly useful for setting parameters. It was one of his papers
I
with
didn't know
published.
that.
So
Oh my gosh.
yeah,
I'm
it's one of
learning
his
so
another
many
look
things.
papers.
Oh my goodness. I have to read that one now. All right. Is there anything else, Mark, that you wanted to bring up before we wrap?
I don't think so. It's yeah, like lattices, like people seem very concerned that they might break in surprising ways, and I can't unfortunately guarantee anything about the future in any context.
Sure.
But if you want to see a lot of examples of lattices breaking surprising ways, you can look 20 or 30 years ago because there were many very funny ones.
Yeah.
So
Yeah. That's a good place to do it.
Well,
Okay.
It is a little funny that when we were an audio-only podcast, we did a very visual discussion of lattices, and now that we are a video podcast, we did an entirely audio discussion of lattices, where some visuals probably would have helped a lot.
Yeah. Sorry about that.
That's not your
No,
fault.
you were doing a great job with the linear algebra actually, and I mean I understand. Yes,
It's the rotations.
exactly.
This is the most fun that Deirdre has had on one of these episodes where we weren't just talking about isogenies.
Yeah, well, oh, and that's another one where you're like, oh, you lattices don't just show up in lattice-based cryptography; they show up in a bunch of cryptography, such as isogeny-based cryptography, like ski sign.
We all know
I was
has
doing-
worked out great.
It's totally great. It's fine. Nothing. Don't worry.
Well, I mean,
about
even
it.
like, this is something like trying to define what lattice-based cryptography is was something I was thinking about today because it's like, well, it's cryptography like based on lattices. Any elliptic curve over the complex number is a lattice,
Yes.
or a rank 2 lattice. So
Yes.
it's like, is elliptic curve cryptography
This is why
lattice-based
you can't-
cryptography? No, that's very stupid. But
This is
it's
why you
hard
can't
to
look
define what
anything
it
up in
is.
Wikipedia. Because everything in Wikipedia is written that generally.
Yeah.
You're the problem.
All right.
I think
I for the record, I would, if anybody has a good definition of lattice-based cryptography, I'd be very interested in hearing it because I've been trying to think through it and I keep running into these weird cases where it's like, oh, if Schnorr's factoring algorithm worked out, would RSA be lattice-based because the best attacks are lattice attacks? Are elliptic curves lattice-based because elliptic curves are lattices? There's got to be some definition somewhere, but I haven't found something that makes sense to me yet, besides it being like this socially defined research area.
you might need to write that blog post. Cool.
Yeah.
Thank you, Mark. Security, cryptography, whatever is a side project from Deirdre Connolly, Thomas Tachek, and David Adrian. You can find the podcast online at SCW Pod and the hosts online at Durham Cresselum, at TQBF, and at D Adrian. He's got the new handle. You can buy merch online at merch.securitycryptographywhatever.com. If you like the pod, give us a 5-star review wherever you rate your favorite podcast. Thanks again to Teleport, who is sponsoring our event in Las Vegas between Black Hat and DEF CON. There are links on our website about trying to find us in the liminal space between Black Hat and DEF CON in Vegas this year in a couple of weeks. Thank you for listening. All right, let's hit the button.
That was awesome.